In this video, we're going to look at two new functions, a quadratic function and an exponential function. We've seen quadratic functions in grade 10, but we may have never seen exponential functions, so this one might be new to us. To know if a function is quadratic or exponential, we can just look right at the equations. We've talked about the degree of an equation before, and we know the degree of an equation is the highest exponent of the variables. So in this case here, we can see the highest exponent of x is 2. So that means that the degree is 2. The y has a degree of 1, so the entire equation has a degree of 2. That's the highest exponent on the variable. We can tell if something is quadratic by just taking a look at the degree of this equation. If the degree of our x variable is 2, we know it's going to look quadratic and it's going to be a parabola. Exponential relations, on the other hand, they don't have a degree, or we don't usually use degree to describe them, because look at the exponent of an exponential relation. The exponent isn't a number, it's a letter. This is what makes an equation exponential. If the exponent is the variable, not a constant like 2 or 3 like we have here. Here we can see the exponent is just the number 2 or the number 1. Here the exponent is a variable. Before we take a look at the graphs of a quadratic and exponential equation, let's look at just the equation now. So I want to know what's the degree or the classification of each of these here. So here, if we take a look at this equation, our exponent of x is 1, our exponent of y is 1. The degree is 1, and we know a degree 1 equation is going to be linear. How about the next one? Here we go. We've got a y term that has degree 1. And then if we take a look at the x, the highest exponent of x is 2. So the degree of the entire thing is 2, which means that this is going to be quadratic. How about the next one? What's the exponent in this guy here? The exponent of y is 1. What's the exponent of this thing? It's x. Whenever you see a letter or a variable as the exponent, this is what an exponential relation is, because the exponent is a variable. How about this one? Here again, the exponent is x. It's a variable, so this one's also going to be exponential. What about the next one? -2, then we have 5 to the power of x minus 1. Still, even though it says -1 here, the exponent involves a variable. Therefore, this one is also exponential. How about this last one here? It looks like the degree is 1 because the x variable has an exponent of 1 here and 1 here, and so does y. But if we expand this, then this is going to be x squared plus 1x plus 2x plus 2. And if we simplify it, the highest exponent of x is going to be 2. So this one is quadratic because it has a degree of 2. Now let's take a look at the graphs of a quadratic equation. So I could tell you that this is quadratic just by looking at the equation, because I see that the highest exponent in the equation is 2. And if the highest exponent is 2, so the degree is 2, and that's on the x variable, then it's going to look just like a parabola. So if the squared was on the y, it's going to look different. But if our degree is 2 and that highest exponent is on the x variable, then it's going to look like a parabola. So one characteristic of a quadratic relation is its graph will be a parabola. And we know a parabola can either open up or open down. Those are the only two options. If it opens to the side, it's not a parabola. It's an inverse of a parabola. Let's come up with the domain and range of this guy right here. So this isn't what all parabolas look like, but this is this particular parabola. So let's come up with the domain and range of this particular parabola. So we know that if generally a a graph is going right to the edge of the graph, we can assume that this is going to continue on. So I'm going to put little arrows, and we know a parabola is going to keep on going up, 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 up. So what's the domain of this thing going to be? Instead of writing this down here, I'm just going to write it up here. The domain of this is going to be, well, what is x allowed to be? X can be 0, x can be 1, 2, 3. Can x be 10? Yes, because this parabola is going to keep going, going, going. X can be anything positive. It can also be anything negative. So x is an element of all real numbers. And this is going to be true for all parabolas. All parabolas. There will be no restriction on. How about the range now? What is y allowed to be? Well, can y be anything? Well, no, because if I plug in 0 here, it doesn't hit the parabola. Nothing down here will hit. When does y start existing? Here, at 3. So y can be 3, 4, 5, 6, and so on, so on, so on. So y is an element of all real numbers. It can be any tiny little number, but y has to be greater than or equal to 3. So for all parabolas, our domain will be, x can be anything. Our range will slightly differ. It will look like this. We'll start that y is an element of all real numbers, but there will be some restriction on y. If it opens up, then y has to be greater than a certain number. And if it opens down, then y is going to be less than a certain number. Let's take a look at an exponential relation. If you were to throw this equation into Desmos, this is what it would look like. It sort of looks like half of a parabola, but instead of rising up on the other side, it's just going to go closer and closer and closer and closer to whatever this line is. In this case, this is the x-axis, or another way to talk about the x-axis is the line y equals 0. So I'm just going to put a dotted line here that this is the line y equals 0. It's also the x-axis, but if we're going to talk about it as an equation, what is true along this entire line here? At every single point, x is changing, but y is equal to 0. That's why we call it y equals 0. So what's actually happening here, if we zoom in on Desmos, is this function is coming really, really, really close to the line y equals 0, but it's not actually touching it. It's hard to see from here, but if you look on Desmos and you keep zooming in and zooming in and zooming in and zooming in, this equation, or this graph, never actually touches the line y equals 0. This is what we call an asymptote. That's how you spell it, an asymptote. What an asymptote is, it's an invisible boundary that the function will come close to but never, ever, ever touch. So we say that it's a boundary that the function will approach but never touch. So all exponential relations will have an asymptote. They will not always be at the line y equals 0, but they will always be horizontal. So that is one characteristic of an exponential relation. All exponential relations will have a horizontal asymptote. So one other point that we want to make about the graphs of exponential relations. By the way, we'll understand why there's an asymptote when we go into the table of values for these guys. But it's important to know that every single exponential relation will have this asymptote. So also an exponential relation will either be increasing this way, or it could also be decreasing. It could also look like this. So no matter what, an exponential relation will not decrease and then all of a sudden start increasing like a parabola. Or if it's increasing, it won't all of a sudden start decreasing. It will either be increasing or decreasing. Let's do the domain and range just of this guy right here. So it'll be the final characteristic that we look at. So let's talk about domain, knowing that these are going to continue on and on forever this way. What can x be? X can be 0, 1, 2, 3, 4. Can it be 10? Well, yes, because this is going to keep on going up, 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 up. It will hit 10, it will hit 100, it will hit 1,000,000. So it can be anything positive, and then we can see it's going to be anything negative as well. This curve is going to get closer and closer and closer and closer to the x-axis, or the line y equals 0. And then it will, we'll just keep on going closer, closer, and closer forever. So that means that x can be any tiny little number, so we know how to write that. We're going to write that x is an element of all real numbers. How about y? What is y allowed to be? So let's talk about all the positive numbers. Can y be 1? Yes, 2. Yes, 3, 4, 5. Continue, 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 continue. Y can be anything positive. How about negative? Y be anything down here? No. So how are we going to write that? We're going to say that y can be any tiny little number. Y is an element of all real numbers, but y has to be greater than 0. Can it equal 0? Can it equal 0? So if I pull from 0 here, is it ever going to hit it? It looks like it's hitting it right here, but by the definition of an asymptote is a boundary, usually a line, that a curve will approach but never touch, which means that if there's a boundary at y equals 0, this curve is going to get so close to 0, but it's not actually going to touch 0. So y has to be greater than 0, not equal to. And this is what all exponential relations will look like. It will have a domain of x can be anything. You can plug in anything you want in there for x. But y will have a restriction. It's either going to have to be greater than some number or less than some number, because an exponential relation could do that too. So it's either going to be greater than some number or less than some number, wherever that asymptote is, and it will not have an equal to sign there. Let's take a look at what the table of values of a quadratic and an exponential equation will look like. So we know how to come up with a table of values if we're given an equation, because all we have to do is plug in random x values into here and see what pops out for y. So I've already chosen these x values for you, but you can choose any x values that you want. So we'll do the first one slowly, and then you'll try the rest of them on your own. But we're just going to take, every time I see an x, I'm going to replace it with -2. So I'm going to put -2. And then squared minus 3, and we're going to check what that is in our calculator. You should get 1. So when I plug in -2, I get 1. I'm going to do the next one. I'm going to plug in -1. We'll do one more, and then you should be able to figure out what to do next. Take away 3. And we should get -2. So I'm going to put -2. So fill in the rest of these on your own, and then come back to the video to check your answer. So if you're coming back to the video, here's what your answer should be. Ta-da! All right, so what I want us to be able to remember about quadratic relations is how to tell if something's quadratic from a table of values. You can figure that out just from the relationship of the y values. So we talked about linear relations before. A linear relation, if we find the first differences, so we're finding the differences one time in the y, we should get a constant number. For a quadratic, it's going to be a little different. So we're going to find the first differences first. So that means we're going to subtract y one time. So how do I get from 1 to -2? We're going to take away 3, subtract 3. Another way to do it is do -2 minus 1, you get -3. How do I go from -2 to -3? We're going to subtract 1. Again, another way to do it is -3 minus -2, we get -1. And then continue on. How do I get from -3 to -2? We add 1. How do I get from -2 to 1? We add 3. So as you can see, the first differences are not the same. And we know this because it's not linear. It's going to be quadratic. For a quadratic relation, we're going to check the second differences. So that means we're going to subtract the y's one more time. So by subtracting, what we're really saying is, what do you add to -3 to get -1? And you adding +2. Another way to think about it is -1 take away -3 is going to be +2. Next one, how do we get from -1 to +1? We're also adding 2. How do I get from +1 to +3? Adding 2. And here we can see that the second differences are constant. They're constant and non-zero, so they're not 0. So if the second differences are constant and not 0, that means that this is going to be a quadratic relation. So here's a note that a quadratic function will have constant and non-zero second differences. That's how we can tell from a table. How about an exponential relation? So remember, it doesn't matter what equation you're given. It could be something you've never seen before. You can always create a table of values and then a graph from that by just plugging in random x values. So I picked some that are negative, some that are positive, and 0, just to see what this thing's going to look like. So I'm going to plug this guy in. So for the first one, we're going to take y equals, instead of x, we're going to put in -2. So what does this mean? If you've dealt with negative exponents before, you know that this actually just means 2 squared, which is going to be 1 over 4. If you've never seen that before, don't stress about it. You're just going to throw it right into your calculator. So if you were to put 2 to the power of negative 2 right into your calculator, you should get 0.25. So that's what I'm going to write here. We got 0.25. Let's do one more. So I'm going to plug in negative 1 into our equation. So this is going to be 2 to the power of negative 1. Again, if you've dealt with negative exponents before, you know that just means 1 over 2. If you haven't, we're going to cover it in the course later, so don't stress about it. If you throw it into your calculator, you will get 0.5. We'll do one more. 2 to the power of 0. What would that be? It's just going to be 1. So we're going to put a 1 right there. So at this point, pause the video, try these two, and then come back to the video to check your answer. So if you're coming back now, you should have answers for these two. And here's what you should have. So let's talk about the relationship between these numbers here. So if you try to find the first differences, there will be no pattern. And if you try to find the second differences, there will be no pattern. That's why I left these columns here for us to try it. But you can try it on your own, and there's going to be no pattern. Then you could try to find the third differences. So you can find a third time, and there will be no pattern. There will be no pattern between these y values by subtracting or adding. The pattern will be from multiplication and division. So when we are subtracting, or figuring out what are we adding every single time, those are called the first differences. If we're going to figure out if there's a pattern with multiplying and dividing, we call that a common ratio. So we're going to look to see if there's a common ratio between each of these y values, and we know ratio comes from division. So what we're going to ask ourselves is, instead of what are we going to add to 0.25 to get to 0.5, my question is, what are we multiplying 0.25 to get to 5? And that answer is 2. We're multiplying by 2. You can find that multiplication by 2 by also dividing from the bottom to the top. So if we take 0.5 divided by 0.25, we get 2. So that must be what we're multiplying by. What do we multiply 0.5 by to get 1? Again, 2. If you can't see that, then go backwards. Take 1 and divide it by 0.5, and you get 2. And so on and so on. So how do I get from 1 to 2? I times it by 2. How do I get from 2 to 4? I times it by 2. So a ratio is determined by division. We divided 1 divided by 0.5 to get 2, etc., etc. And it is a ratio they all have in common. They all have 2 in common, which means that this relation does have a common ratio. And if it does have a common ratio, then that means it is exponential. So here's a note that an exponential function will have a common ratio. Last, let's sketch these two equations, these exponential equations, and see what they'll look like. So we're going to sketch this guy first, and we actually already have a table of values for that guy because we did it up here. Ta-da! Okay, so what I'm going to do is first going to copy down the table of values from above. So now that I've copied my table from above, I'm just going to put a label that we are finding y is equal to 2 to the power of x. So this is the first guy that we're doing. So now I'm going to plot those points onto my graph here. So my first point was -2 and 0.25. So 0.25 is going to be hard to sketch, but we can do it. So -2 is here, -1, -2, and 0.25, I'm going to put a dot right above the x-axis here. Something similar to that. And then we have -1, 0.5. So I'm going to put a dot right over here, right in the middle. And then the next we have 0 and 1. And then we have 1 and 2, and 2 and 4. If we wanted to do 3, it would be 3 and 9, and it would continue like this. So now that we know that a exponential equation will have a asymptote, we don't know how to find the asymptote just yet, But right now, the only asymptotes that we have seen have been along the x-axis. So that's what I'm going to draw right now. I'm going to draw a boundary along the, along the x-axis at the line y equals 0. We will learn where those asymptotes are, but for now we'll just use Desmos to find them. And then I'm going to connect this guy, making sure to put arrows at the end, and making sure to show that this thing is going to approach the x-axis but not touch it. Now we can better understand why there is an asymptote right here. Why can never be greater than 0? Because look at these numbers here. I can plug in anything for x. I can plug in negative numbers. I can plug in 0. I can plug in positive numbers, so I'm plugging them into here. Is there any number I could plug into x that would give me a negative y? I tried plugging in negative numbers. Does it give me a negative y? Nope, it's positive. And that's just, we know it's positive because of an understanding of exponents. If you've never learned that before, we'll get into it. But I've tried negative numbers and the answer still comes out positive. I've tried 0 and the answer comes out 1. I've tried positive numbers and the answer comes out positive. That means there's no x that I could plug in here that would give me a negative number. So that means in our graph, y is always going to exist above the x-axis. That's why there's an asymptote here. There's nothing I could plug in for x that would give me a negative y. So y has to exist entirely above the x-axis. How about an equation like this guy? Y equals 0.5x. So how will that graph differ? So I'm going to start a t-table. We're going to plug in our x values and see what comes out for y. So I've set up our t-table. We're going to plug in these values for x into this equation, see what comes out for y, see what happens. So if I plug in negative 2 here, 0.5 to the power of negative 2 is going to be, 4. How about 0.5 to the power of negative 1? That's going to be 2. 0.5 to the power of 0 is going to be 1. 0.5 to the power of 1 is going to be 0.5, and 0.5 to the power of 2 is going to be 0.25. So let's sketch that. So our first coordinate is when x is negative 2, y is 4. So let's plot that. Next one is negative 1 and 2. Then we have 0 and 1, and then we have 1 and 0.5, and 2 and 0.25. So we don't know any other asymptote than y equals 0, so I'm just going to write this in here, that there's an asymptote at y equals 0. We'll talk about later when that asymptote moves. So I'm going to connect these all with a smooth curve, and I'm going to make sure that I'm just approaching, that wasn't perfect, I'm going to do this again. Smooth curve, here we go. I'm just approaching this axis. My curve isn't perfect, but there we go. So what's the difference between these two here? Well, one of them is increasing and one of them is decreasing. Why? What's the difference between them? The difference is this base. This has a base of 2 and this has a base of 0.5. Why are they so different? Well, think about it. If I have a base that's bigger than 1, as I put bigger and bigger x's in there, the number's going to grow and grow and grow and grow. So for example, 2 to the power of 1 is going to be 2. 2 to the power of 2 is going to be 4. 2 to the power of 3 is going to be 8. By the way, I had a brain fart here. I don't know why I put 9. I'm just going to erase this. This should be 8. And then 2 to the power of 4 is going to be 16. So as I put bigger and bigger x's in here, the number is going to grow and grow and grow and grow and grow. So if we have a base in here that's bigger than 1, then our relation is going to be increasing. But what about if the base is less than 1? So 0.5. By the way, with an exponential relation, the base has to be greater than 0. Otherwise, it doesn't look like it's not an exponential relation. So we're talking about bases between 0 and 1. So 0.5. If I put 0.5 to the power of 1, it's going to be 0.5. But if I do 0.5 to the power of 2, well, that's 0.5 times 0.5. That's really just saying what's half of 0.5? It's going to be 0.25. As I keep multiplying this number to the power of 3, to the power of 4, to the power of 5, 0.5 keeps multiplying by itself, and the numbers can get smaller, 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 smaller. So the conclusion is, if our base, so if we're going to call B our base, if our base is greater than 1, then the graph will be increasing. And if our base is less than 1, but also has to be greater than 0, otherwise it's not an exponential relation. So we're talking about 0.5, 0.25, 0.99, any numbers between 0 and 1, then the graph is going to be decreasing. Which is why when we had a base of 2, our graph increased, and a base of 0.5, our graph decreased.